Hello, a great welcome to this series on PLAXIS. Myself Jarajan P. This is tutorial number 4 and it will demonstrate the calculation of the stresses as well as the displacement under a shear wall foundation. This tutorial will be basically presented in two parts, part 1 and 2. This is part 1 of the tutorial. So let us straight away go to the problem statement. So the geometry of the foundation that is supporting the shear wall and two columns is shown here. Essentially, you can see that on this side we have got a larger portion of the foundation, which is essentially of a dimension is 8 by 9 meters, and it also supports two vertically a lot of the columns as well. So the entire foundation is supported on a sand strata of a depth of 20 meters. So you can see that the bottom of this foundation is at minus 20 meters. The groundwater is considered at the ground level. So here, as you can see that the shear wall is basically is a lateral load carrying element, whether it is a wind load or shear load. Accordingly, we need to transfer the vertical load, horizontal load, as well as the moment from the shear wall to the foundation. And these two columns are essentially the gravity loading members only, that's a columns. So accordingly, as you can see that only vertical loads are applied at these points. So the soil domain that will be modeled in this tutorial will be 80 meters by 40 meters. So the soil parameters considered for the tutorial are given here. The material model used is a Moore-Coulomb filter criteria, and drainage type considered is a drained one. The unit weights in the saturated and unsaturated condition are considered as 18 and 16 kg per meter cube. Coming to the stiffness, the modulus of elasticity of the soil will be taken as 10,000 kN per meter square with a Poisson ratio of 0.25. The strength parameters include a coefficient intercept C of 1 kN per meter square, friction angle phi of 32 degrees, and a direction angle of 2 degrees. Now coming to the footing and the shear walls, both will be modeled using the plate set available in the PLAXIS, and the material model used will be linear isotropic. And the unit weight of the concrete material is taken as 10 kN per meter cube. And the raft will have a thickness of 0.6 meters, whereas the shear wall will have a thickness of 0.2 meters. The E value of the concrete material is taken as 25 into 10 raised to 6 kN per meter square with a Poisson's ratio of 0.15. Now, in order to effectively transfer the moments to the base, we shall make use of the rigid link elements, and to create the link elements, we will make use of the beam members available in the PLAXIS with an area of 1 meter square, and the unit weight will be taken as 0, and with an E value of 25 E6 kN per meter square, and with a moment of inertia I20, I30, 1 meter raised to 4. So let us start the PLAXIS. As usual, let us start with the title. We'll just fill up shear wall foundation. Shear wall foundation. We'll proceed for the model contour parameters. We'll keep all the default units the same, and x minimum will set it as minus 40, and the x max will keep it as 40, so that the total model length will be 80 meters. And then here y will be, we'll keep it as a minus 20 y minimum, and the y max will keep it as a plus 20, so that the other width will be 40 meters. So this is okay for us. Now let's proceed for defining the stratigraphy using the borehole facility. So let me just zoom this origin location. So we shall place a borehole right at the origin. Okay. So let us start adding the soil. As you know, we have got only a single layer, so we can keep the top as a 0 and the bottom will be say 20 meters deep, so we'll have it as a minus 20, and the water table will generate the surface. Accordingly, the head will be provided as 0. So this means that the stratigraphic definition is complete. Let us proceed for defining the soil material. We'll click materials, and we'll create the subtype as soil and interfaces, and click here new. So let us start defining the material set identified. It will be identified by the under the name sand, for example, and the material model will be Moore-Coulomb. The drainage type will be the drained, and the unsaturated and saturated will be 16 and 18 kN per meter cube. Okay, so now let us proceed for the parameters. The parameters will keep it as, for example, 10,000. That is a 1E4, and that is a Young's modulus of the soil, and the Poisson's ratio will be 0.25. Coming to the strength parameters, will keep the reference coefficient as 1 kN per meter square with a phi value of 32 degrees and an associated dilation angle of 2 degrees. So that's okay for us. So okay, fine. So now let us just drag and drop this sand material onto this borehole. So thus we find that the material is already assigned to the model. That's okay for me, and this is okay, fine. So now let us see the model. Yes, this is the uh, soil model with the material being already assigned to it. Now let us proceed for creating the surface that represents the foundation, and this will be obviously done in the structures module. So we shall go to the structure modes, and we shall define the surface through the facility known as the surfaces, and then we shall later convert this surface into the plate. So let me just zoom this a little bit so that we'll be able to place the foundations properly. So let us create the surface. So to create the surface, what we can do is that we can just arbitrarily uh, select the points, and then later we can finalize it. So we can just pause it over here. Okay, this is one point. This is the third. We'll just go on creating the surface. So finally we'll close at this point. Okay, so now let us start editing these points so that we find that yes, the surface basically represents the geometry which we wanted. So let us start editing this the various coordinates. So first one will be minus of 5 and with a minus 4. And please remember here we are going to generate this surface on the top. Accordingly, all the set coordinate will be 0. Let us proceed for the second point, that will be minus 4.44, minus 4.44, and then the third one will be 4.44, 4.54, 4, and the fourth one will be 4.5, 1.5, 4.5, 1.5, 4.5, 1.5, and the fifth one will be 15.5, 15.5, and then 1.5, 1.5, and the sixth node it will be 15.5, 15.5 with a minus 1.5, the minus 1.5, and the seventh node will be 4.5 minus 1.5, 4.5 minus 1.5, minus 1.5, and the eighth node will be 4.5 minus 4, 4.5 minus 4, minus 4, and finally we have to put the ordinate of the same first point back over here as minus 4.5 and with a minus 4, minus 4. So that must be good enough for us. So this is okay. So you can say that yes, we have created the surface. So that represents basically the raft foundation supporting the shear model and the two columns. So let us first create the surface, convert the surface into a plate. So we'll create a plate out of this. Accordingly, you can see that the plate directions have already been assigned over here. If you want to see this surface foundation very close, so this is the shape which we wanted. Now we want to assign a plate property to this. So let us proceed for defining the property of the plate material representing the foundation. So this can be done through the set type. We'll go to the plates and we'll define a new one. And let me call it as, for example, this is my footing. Okay, and the d value, the thickness of this raft, that will be taken as a 0.6 meters. So this is my 0.6 meters. And the gamma I will take it as 10 kilonewton per meter cube, and the material that will be used will be a linear isotropic material, and here the e value will be, say it is a 2.5 e7, and the mu value will be 0.15 value will 0.5, which means that the definition of the plate property is complete. So let us assign a proper color to this. So I would like to have a yellow color over this. So this is my plate. Okay, so this my plate means I will assign this color. Okay, okay, fine. So means that the footing property is already defined. This is okay for us. So we shall just assign this property to this plate. So we shall go to this set material and the footing. So accordingly you will find that yes, the color of this material is already assigned to the plate. So having defined and assigned properties for the mat foundation, now we shall proceed for creating basically the shear wall, and the shear wall will create from 0 meters up to an elevation of 3.0. Okay, fine. So let us first draw the four lines that represents the footprint of this shear wall on the foundation. So we can just straight away create the lines. So I have already set the snap settings so that I can directly take care of the points spaced at zero point 0.5 meters. So this should start at minus 1.5, minus 1.5, so minus 2. So I can just move this cursor so that I can see the coordinates directly over here. So then I will move to this point that represents basically say 1.5 and a plus 2. I will click over here. I will create another line which represents this is at minus plus 1.5 and 2. I will click over here. Then I will have a at 1.5 and minus 2, and I will go back over to the same point that is a minus 1.5 and a 2. So you will find that yes, we have generated four lines that represents the footprint of this shear wall. So for example, if you go to the geometry and see the lines, you can say that yes, we have the four lines. So if we just go on clicking it, now what we do is that we'll select all these four lines and then do the extrusion process so that we'll be able to create the shear wall at a stretch. So let us just go on. So press the control key, go on selecting the various lines. So we have selected the four lines as you can see. Just to proceed for the extrusion. Now I want to take this four lines up to z equal to 3 so that I generate a shear wall of length 3 meters. So I will just proceed as a 3, so that's okay for me. So you can see that this extrusion direction, so this is applied. So you can say that yes, we have generated the shear wall for just using the four lines. Now let us if you go over to this surfaces, you will find that we have now the four surfaces that's already selected. Now let us just create the plate out of this. So you can see that yes, we have created the plate. Okay, now we need to define the material that is required for the shear wall. So this can be easily done because we know that this property is exactly the same as the base mat. Only difference is that the thickness of the shear wall is at 0.2 meters. So we shall go straight over to these materials, and the materials let us go straight to the plates, and the plates we can just copy this footing, and we can just copy this, and so let us call this as for example the wall, and we know that all the parameters will be the same exactly. Only thing is that this shear wall thickness will be 0.2 meters, and let me just change this thickness, the color of this wall, so that I will be able to easily. You can see that yes, we have correctly modeled the wall, defined the material for the wall. So if you double click, you will find that the only difference is the thickness 0.2 meters, and the unit weights, E values, and the Poisson's ratio is the same. Now let us straight away go for assigning this material to the place selected. So we'll set the material, and this will be my wall. Okay, so you can see that yes, all the wall color is now turned uh, green. So this means that the shear wall development is complete, and we have assigned the right material to it. Now what we are going to do is, now we are going to create a rigid element. Unfortunately, to my knowledge, I don't have any kind like to create a rigid joint in this version, which I am using. So what I have decided is I have decided to create rigid links using the beam facility available in PLAXIS so that I will be able to transfer all the vertical load, horizontal load, and moment correctly to the base level. Okay, so let us first define the point. Okay, at the 3 meters above the shear wall level. So I will just go over here. I will create the point over here, right? I'll just select a point. Just click it. So you can change it over here. I will keep it at a 0. I'll keep it at a 0, 0, and I'll generate it at a 6 at z equal to 6 meters. Okay, z equal to 6 meters. This means that I have defined the point. As you can see that this is my point. So if you see over here points, you can see that this is the point 6 that represents my point, and this point what I'm going to do is that I'm going to now define, okay, the members that represents the rigid links, okay. And for this what I will do is I will create 8 numbers of beams, one each at the corner of this shear wall and one each at the midpoint of this shear wall parameter, and connect these to the reference point which I created right now, that's a point 6. And then we will assign these rigid beams a property as well. Okay, so let us proceed for creating the first rigid beam. So we will make use of, just press this button, okay, create a line, and here you will find that there's a option to create a beam directly, okay. So you need not to worry about this coordinate, just select the 2 points, okay. So now you will be able to edit these points. I want to keep it at from say from 006, 006, 6, okay. And now I want to draw this, point it to this, from this point to this corner, and obviously we know that this corner is nothing but it is my say minus 1.5, okay. And my y point, it should be say minus 2, and my z will be 0, okay. So let me say that yes, z will be, this should be 3 meters. So yes, you can see that now a beam is placed from this reference point to the corner. In a similar way, what we'll do is that we'll go on placing 7 other beams in a similar way. So in a similar way, you can see that we have placed all the balance link elements. So there are total 8 link elements, as you can see. Now we need to assign some property that represents a rigid link. So let us start creating a property for this link beam elements. So we'll go to the materials, and the materials will go to the set type as the beams. And the beams, you can see that right now we don't have any materials defined, so click the new. So you can call it as, for example, the link and let me choose a proper color for it, okay, fine. And then the area, as we already discussed, 1 meter square is okay, and the unit weight, so just a link element, I will keep it as 0, and the e value will keep it as a 25 e6. 25 E6 is the E value, and then regarding the I3, I will assume values of I2 is equal to I3, each is equal to 1 meter raised to 4. So that's okay for us. Now we need to assign this particular link material to all the elements or the link elements. So what we can do is that we can go to the lines, we can just select all, for example, line 5, as you can see that when we highlight it, this member is created. So in a similar way, press the control and go on selecting all these line elements, okay. And then what we need to do is that we need to assign to all this the so-called link beam material. So if you press beam, you can see that set material, in the set material select the link which is already defined. So as you can see that yes, every beam element is now assigned with the link element. So for example, if you go to the beam, go to material, you can see the link, and if you go to material, beam 8 material link, so we have got total of 8 beams, and each beam is associated with the link element. That's good enough. So we have completed the definition of the link elements, and now we need to define point loads at some critical locations. For example, at set equal to 6 meters, we need to define a point load. At other column location also, we need to define a point load. So let us proceed for the definition of the point loads. So obviously, we can go over to this point, okay, create point. So there's a point load option, create point load. You can press, for example, here, and if you want to change, you can change it as, for example, I wanted to apply it as 0, 0, 0, 0, okay, at set equal to 6, at set equal to 6, okay. So you can say that yes, a point load is already defined at this point, and right now you can see that PLAXIS by default has assigned a -1 kilonewton downward only. Okay, we will update all these loads in the corresponding stage construction. Now we need to define 2 column point loads also. So we can, in a similar way, we can go over here, create point load. Okay, we can, for example, just click a point over here. You can adjust this as coordinates straight away over here, and this point will be 6.5. So this will be 6.5, and y and z are all equal to 0, and we have defined a unit load again here. So f z equal to -1, and please remember we have got one more column load to be defined, that is somewhere at this location. So in a similar way proceed. So we can let us go with the definition of the point load once again. So I will just click at some point over here. So I'll adjust the coordinate over here, and this coordinate we know that it is at 13.5. Okay, 13.5, 0, that's okay. So you can see that yes, right now a unit load is also placed at another column location, and all these column loads will be explicitly defined during the corresponding stage, construction stage. So now, so we have defined the point loads as well. Now are very ready to proceed to the mesh module. So let us proceed to the mesh module. And in the mesh module, we have to do a little bit of a fineness for the what we call as the foundation element. Okay, so let me just go to the geometry over here. I want to keep the volumes off so that I will be able to see the other elements properly. So let me first select this foundation element. You can see that right now the fineness factor is 0.5. I want to refine it further. So what I can do is that I can press this refine mesh option and just go on double click it 0.35, 0.25, 0.17768. This is okay for me. So I will refine this foundation element first of all, and next I will go for refining the so-called my wall elements. So let me just select this element. Okay, right now you can see that it is at 0.5. I'll just refine it to say 0.25. That's okay. I'll select the other element, this element, and here again is 0.25. I want to refine it further to 0.25. 0.25, that's okay. Now I will select the third wall element. This is my element. Okay, so it's again 0.5. I want to refine it. So I will refine to, you can say that 0.25 again. Now one more element is left. I will select it. You can see that it's a 0.356. I want to refine it further to the 0.25 level. 0.25 level. Okay, that's good enough. So the local refinement is complete. Now we can go for the global defining the global coarseness. We'll select the global coarseness as medium. So this is okay for us. So you can see that the meshing is in progress, and we will be able to see the completed mesh. So please remember, if you want to refine again the elements very near to the soil, near to the foundation element, we can define additional surfaces and then assign some local coarseness to the surface, which immediately brings a lot more fineness to the corresponding soil volumes. Okay. Now let us proceed for seeing the refined mesh. So you can see that yes. Okay. I'll just zoom in a little bit so that I will be able to see the. Okay, you can see that yes, this is the meshed what we call as the raft element, and this is the meshed wall element, and you can see that the coarseness is a little bit larger for the soil element, and that's what I was talking about. If you want to bring some more fineness to the soil immediately around this raft foundation, this can be done immediately by defining additional surfaces and then bringing some local coarseness to those surfaces, which ensures that much more refineness is brought to the soil immediately near to the foundation element. So this means that mesh operation is complete. We can straight away go to, I think, the staged construction. So the details regarding the staged construction and the review of the results, including the settlement and the stresses below the raft foundation, will be taken up in part 2 of the module. Till then, bye.